Hello everyone, welcome to our differential equation class. In this video we are going to solve the heat equation with non-homogeneous boundary conditions of Dirichlet type. So first we are going to introduce what do we mean by non-homogeneous Dirichlet boundary conditions for the heat equation. Then we are going to see that the solution of these problems do not satisfy the superposition property, and that was an important property to find solutions of the problem. So what we are going to do to solve the heat equation with non-homogeneous boundary condition is to transform this problem into a problem with homogeneous boundary conditions. And to do this transformation, and there is an important function that we need to introduce, and this is the equilibrium solutions of the original problem of the heat equation with non-homogeneous boundary conditions. So essentially this is the plan for today, to solve the heat equation with non-homogeneous Dirichlet boundary conditions. Let's start introducing non-homogeneous Dirichlet boundary conditions for the heat equation. So a non-homogeneous Dirichlet initial boundary value problem for the heat equation is to find the function T, a temperature, function of time and position, solution of the heat equation is right here. So the heat equation, for the heat equation we need a constant alpha, which is positive, the thermal diffusivity of the material, and we solve the heat equation in the usual domain, T between 0 and infinity, and the variable x in 0L, the size of the material, L is positive, and we need to solve the heat equation together with boundary conditions, which are of the form Dirichlet boundary condition, because we fix the temperature on both sides of the material for all times. And now we fix these values of the temperature to be T0 and TL. And now T0 and TL are arbitrary constants. This is also an initial problem because we also satisfy some initial condition, which is the temperature for all time, the temperature at the initial time for all x is a given temperature tau of x. So this problem, the physical situation of the problem is we have a solid material, in this case a rectangular box. We put insulations on the top side, on the bottom side, and then the front side and the back side, and the initial temperature is a function only of x, so all these points in the bar have the same temperature, all these points. So the temperature on these cross sections of the solid material have the same temperature. That's why the temperature is a function of x. When you do all that, one can prove that the solution is going to be also a function of only of x, and nothing is going to depend on x and y. So this is a one space dimensional problem, and now we are putting Dirichlet boundary conditions on this side of the bar and on this other side of the bar. That is, we fix the temperature at x equals 0 and x equal L for all times to be T0 and TL, which they are not necessarily 0. So the non-homogeneous part comes because these two constants could be non-zero. This is what we say here. The non-homogeneous boundary condition is, so the boundary conditions are homogeneous when the constants are 0, otherwise they are non-homogeneous boundary conditions. Now, the separation of variable method does not work with non-homogeneous boundary conditions, so let's put that in red. Does not work with non-homogeneous, so let's put also that in red. With non-homogeneous boundary conditions. And why the superposition, so the separation of variable method does not work? Well, because we do not have the superposition property. So let's see that in a simple example. Suppose that we have two functions, temperature 1 and temperature 2, of two situations of the bar. These are temperatures function of time and position, that they are solution of the heat equation with boundary condition that they are non-homogeneous. Suppose that both functions t1 and t2 for I equal 1 or 2 satisfy the boundary condition that at x equals 0 both solutions take value 3, and both solution at L takes value 7 degrees, 3 degrees. Well, then the sum of these two functions is a new temperature function, the temperature T, but this sum is not going to satisfy the same boundary conditions. Actually, the sum is going to satisfy the boundary condition to x equals 0 to be 6 degrees and here to be 14, because 3 comes from here, 3 comes from here, and you get the 6. So you have here two functions, solution of the non-homogeneous boundary value problem, and the sum does not satisfy the same boundary value problem, it satisfies some other boundary value problem. So we do not have the superposition property. So what is the idea to solve a problem with non-homogeneous boundary conditions? Well, the idea is to translate the non-homogeneous problem into an homogeneous problem. How we do that? Well, let's recall what we did in a simpler case. In a simpler case, for example, second order linear differential equations like this. Equation like this. So the problem was to find y of t, solution of a non-homogeneous equation. Recall the non-homogeneous part is here. This is in principle different from 0. Solution of y, solution of this equation, second derivative times a coefficient times the first derivative plus another coefficient, the function, equal f, and f is non-zero. So how we solve this problem? This problem also does not satisfy the superposition property. You have two solutions of this problem. The addition is going to be a solution with 2 here. So how did we solve this problem? Well, we found a particular solution of this equation, just one solution, and then we realized that we can translate the problem from the function y into a function yh, h for homogeneous, by simply subtracting this particular solution. So we are translating the problem from the function y to the function yh. This function yh, when we do this difference, is going to satisfy an homogeneous equation with equals 0. So this equation now has the superposition property. We know all the solutions to this problem. So we know all the solutions, therefore we can get the function y we were looking for. We are going to do something similar to this idea for the heat equation. So recall, what we do here is we know how to solve the homogeneous equation. We know all the solutions. So we already know this function, so we get the function we were looking for. And what we want to do now is to repeat this idea for the heat equation where the non-homogeneous part is not in the equation but in the boundary conditions. So we are also going to translate the problem by a function, and instead of and the place of the function yp place here is going to be done by a function that we are going to call temperature E from equilibrium. This is going to be an equilibrium solution of the non-homogeneous heat equation. So now our next step is to introduce what this function is, and then we are going to see how we can use it to reproduce this idea, but now for the heat equation. So let's introduce the equilibrium solution for the heat equation with non-homogeneous boundary conditions. The definition is the equilibrium solutions of the non-homogeneous Dirichlet boundary value problem. We don't need initial conditions here, just boundary value problem for the heat equation with non-homogeneous boundary condition. The equilibrium solutions are time-independent solutions of this problem. that we are going to call T temperature sub E equilibrium. So what do we mean by time independent solution? Well, the function solution does not depend on time, so the equilibrium function of time and x actually does not contain time. Suppose you put a function like this into the equation. What is going to happen? Well, this side of the equation is going to be automatically 0. So you're going to be solving the equation for the equilibrium is going to be actually two derivatives. The alpha can be cancelled out, equals 0. So we cancel the alpha. This is the equation for the equilibrium solution. Very simple equation that we know all the solutions. And this is what we say in this theorem. The equilibrium solutions for all the solutions, the equilibrium solution for the boundary value problem with these boundary conditions is unique and is given by this function here, where T0 is this number and TL comes from here, and this is T0, and here we have L. So it's a linear function of x. Why? Because the equation for TE again is second derivative equals 0. And this is what this is the proof essentially. The proof of this result is super simple. The heat equation has this form, obviously. Now we look for time independent solution, so something that does not contain the variable time on the right hand side. Then you put that into the heat equation, and what you are going to obtain is that the equation temperature, the equilibrium temperature must satisfy this equation. This is a function of x, has to be 0. Well, but we know what are all the solutions to this equation. These are linear function in x. So the equilibrium solutions have to be linear function on x, that we are going to call them C1 plus C2x. And now we have the boundary conditions. So if we put the boundary condition here at T0, this is the equilibrium solution at 0. Well, we evaluate here, and this is 0, so we are going to have C1. So obviously C1 has to be the temperature on the 0 side of the bar. Then on the other side of the bar, the equilibrium solution when we evaluate at L has to be TL, but this is C1 plus C2L, and these two things together imply that the temperature on the L side of the bar has to be T0 plus C2L, which means that C2 is nothing more than TL minus T0 over L. And let's raise this a little bit. Well, here we are. We have C1, we have C2. Therefore, we have the equilibrium solution. And the equilibrium solution is what we said in the theorem. It's T0, then the slope, which is going to be TL minus T0 over L, all multiplied by x. And that is the proof of the theorem. So what we are saying in a little graph is that the equilibrium solution, when we have, in this picture we are assuming the T0 is smaller than TL. So suppose this is our temperature on the 0 side of the bar, this is x. And suppose this is the temperature on the L side of the bar. So then the equilibrium solution is a straight line connecting these two temperatures. Now we can introduce the main result of this video, which is how we are going to transform the original problem with non-homogeneous boundary conditions into a problem with homogeneous boundary conditions. And here is the main result. The non-homogeneous Dirichlet initial boundary value problem for the function t, which is to solve the heat equation in the usual domain with non-homogeneous Dirichlet boundary condition given by the temperature on one side of the bar and the temperature on the other side are given by T0 and TL, which now are arbitrary numbers, and with initial conditions where the temperature at the initial time is a given function, tau of x. This is an initial boundary value problem with non-homogeneous boundary conditions. That problem has a unique solution. This is what we are going to say in this theorem. This problem has a unique solution and is given by the function t to be equal the addition of two functions. The function te, which is the equilibrium solution of this problem, plus some other function that we need to figure out what it is. So the first function, te, is the equilibrium solution that we discovered in the previous theorem. So this part of the solution is going to be this linear function in x. What is th? Well, th is the solution th is the solution of an homogeneous Dirichlet initial boundary value problem. Homogeneous is the key word here. So th, we are going to show that is going to satisfy the same heat equation that the original function t satisfies, but now instead of satisfying non-homogeneous boundary condition, th is going to satisfy Dirichlet homogeneous boundary conditions. And now the initial data is for th is not going to be exactly the initial temperature, it's going to be the translation of the initial temperature. So the initial temperature for the function th, the h is from homogeneous, is going to be the translation by the equilibrium temperature of the initial temperature. So this is a Dirichlet initial boundary value problem with homogeneous boundary conditions, so we know what the solution is. th, we have already a formula from a previous video, and the formula is the sum from n equal 1 to infinity of the eigenfunctions on the x part of the solution, these sine functions, multiplied by exponential with the eigenvalue t and the thermal diffusivity here, and coefficients. And these coefficients are computed in terms of the initial condition for th, which is this function, the translation of the original initial temperature. So the ch are going to be given by this formula, where here you put the initial temperature for th, which is this, multiplied by the sine function. So this is our main result, and now we are going to prove it. Let's prove that all we say here is true. And the only thing to prove it is just to write the temperature in this way. And then it's very easy to verify all we have said. So let's do the proof of that theorem. So proof. Let's put it here. Proof. In one page we can write everything, hopefully. So we start saying that we are going to write the original unknown function, which is the temperature of the bar as function of time and position, as the equilibrium solution that we know how to compute, and we have computed already for this problem, plus something else that we call th, that depends on time and x, and here this part of the solution, the equilibrium, is going to be an equilibrium solution of the heat equation, which we know what form they have. They depend on x only, and they have the form T0 plus a slope, which is TL, let's put it here, TL minus T0 over L, all multiplied by x. It's a linear function in x. This is the equilibrium solution of the non-homogeneous problem. Alright, so then what happens when we put this expression into the heat equation? What happens? Okay, to see that, then we need to compute the partial derivative with respect to t of the function temperature. But this is going to be the partial derivative here, which is 0, and the partial derivative here, which stays. So this is going to be 0 plus the partial derivative with respect to time of the function th. Okay, what is the second derivative with respect to space of the function temperature? If we have this form of writing the temperature, when it's going to have second derivative here, so it's going to have t double prime, t equilibrium double prime, plus the derivative with respect to x twice of th. But recall that this is an equilibrium solution, so this is 0. So this is actually the derivative with respect to x twice of only the th part. Alright, so what we just said is, well, let's add the 0 here, just to be clear. This is going to be 0 plus that. Okay, so then the let's say here 1, 2 here more or less, the original function is going to satisfy the heat equation if and only if the function th satisfies exactly the same heat equation. So this is our first conclusion. The function th has to satisfy exactly the same partial differential equation as the original function temperature. But now, what are the boundary conditions for T homogeneous? Well, boundary conditions, the boundary conditions now are, what is T at 0? T at 0 is the temperature at any time x equals 0. Okay, but this is the equilibrium solution at 0 plus the homogeneous part of the solution at any time x equals 0. Okay, but we know that this is by construction T0. So, and here we still have TH. Well, but this proves that cancels with that, and TH must satisfy homogeneous boundary conditions at x equals 0. This has to be 0. And a similar calculation on the other side of the boundary says that if we put the L here, this has to be the temperature for all times at x equal L, but this is the temperature of the equilibrium solution at L plus the temperature of the TH at TL, but by construction this is TL plus TH of TL. So just as before, this cancels that, and then the TH, the temperature H at this side of the bar L also has to be 0. So we have homogeneous boundary condition for the temperature TH. But what are the initial conditions for this function TH? Well, initial conditions, we compute it in the same way. Initial conditions. So tau, we know that tau, the function tau, is the temperature at t equals 0 for all x. But this is the equilibrium temperature plus the TH evaluated at time equals 0 x. Alright, so from here we get what is the initial temperature for the part of the solution called TH of 0x. And this is nothing more than the original initial temperature minus the equilibrium solution. Okay, but so summary. The function that we want to look for, th, satisfies the heat equation. Satisfies homogeneous boundary conditions. dH at 0 at T0 has to be 0. dH at TL has to be 0. And the initial condition is that the temperature at the initial time, 0x, is given. But now it's given by this function, the original temperature minus the equilibrium temperature. But it's given. So this is the problem that TH has to solve. But this is an homogeneous initial boundary value problem, so we know that what the solution is. The solution is that TH of Tx is going to be a sum from n equal 1 to infinity of coefficients, because this is a Dirichlet, homogeneous Dirichlet boundary condition. What we are going to have here is, this is a constant c, we are going to have exponential minus alpha, then the eigenvalues for that problem is going to be n pi over L squared multiplied by t, and then sine functions of n pi x over L. And what are the coefficients Cn? The coefficients Cn are given by the usual formula, which is 2 over L, the integral between 0 and L of the original initial temperature for this problem, which is this difference of two temperatures, so tau of x minus the equilibrium temperature for x. This is the theorem from the previous video, so we are not doing anything new here. X over L dx, and when we put all that, the solution formula is what we have then in the theorem. Then the function we are looking for is going to be nothing more than T0 plus TL minus T0 over L times x plus this sum from n equal 1 to infinity of this coefficient Cn, which are computed by this formula here, then comes the exponential negative alpha n pi over L squared times t, and then comes the sine of n pi x over L, which is what we said in the theorem. So that's it. That's the proof. The translation just works. There. The translation just works. Okay, let's solve one problem to see how this idea works. So suppose we want to find, but here we want to find t, not u. We want to find the function t of time and position, solution of the heat equation. Here we have a particular thermal diffusivity with non-homogeneous Dirichlet boundary conditions. The boundary conditions are at x equals 0 and x equals 5. These are the two temperatures that we have. And then we have an initial temperature given by the function that says the temperature is 2 on half of the bar and 7 on the other half. So essentially something like this. This is our initial temperature for the function temperature of the bar. 0 in the first half of the bar, 7 in the second half, and the bar is go from 0 to L. From 0 to L, and L is 5. Okay, so the first thing we need to do is we need to find the equilibrium solution. Okay, the equilibrium solution is the solution of the equation 0 equal temperature second derivative of x. We need boundary conditions and temperature of equilibrium at 0 to be 2, and temperature equilibrium at 5 to be 7. Alright, so from here we get that the solution, the general solution of the problem, is very simple, and it's a linear function c1 plus c2x, but the boundary conditions imply that 2 has to be equal c2 temperature equilibrium temperature at the point x equals 0, which is c1 plus 0. So we end up with c1 is equal to. Okay, and then the other boundary condition is that 7 has to be the temperature at 5 on the other side of the bar. Okay, but this is c1, so c1 is already 2, so 2 plus c2 multiplied by 5. And that means that we have 5 is equal c2 times 5. So, well, let's put it here. 5 is equal c2 times 5, and therefore c2 is 1. So we got the two constants, and then all this calculation here means that we got the equilibrium temperature. The equilibrium temperature is going to be 2 plus the constant 1, so plus x. Recall that we had the formula. The formula was let's put it here in parentheses, that we have a formula for the temperature in the theorem. What that was, the initial temperature, it was T0 plus TL minus T0 over L times x, isn't it? Well, but T0 is 2 plus 7 minus 2 over 5 x, which is exactly the 2 plus x that we found. So everything agrees. Now we can move on. Now what is the equation for TH? So now once we have the equilibrium solution, we write the temperature of function of T and x. We write it as the equilibrium solution, which is 2 plus x plus the rest, which is going to be TH of Tx. So this is how we translate the problem from the original temperature to the homogeneous temperature TH. And what is the equation for TH? Well, the derivative with respect to T of TH is nothing more than what? So we put we compute the T derivative here. This is going to be 0, and this is going to be equal to the T derivative here. Or let's do it like we did it in the theorem. The derivative with respect to T is nothing more than 0 plus dt of TH. The derivative with respect to x twice of T is, because it's second derivative with respect to x, this is 0, and is equal the second derivative with respect to x of TH. So the heat equation for the function temperature, which is if the function T satisfies the heat equation, T is equal 3 second derivative with respect to x of T. Well, we can replace this by that, we can replace this by that, and that implies that TH satisfies the same equation. Let's put it here, dt of TH is 3 dx twice of TH. Okay, satisfies the same heat equation. And now what are the boundary conditions? well, the boundary conditions for the H are, so actually the boundary condition for the temperature is 2 has to be equal to the temperature at T0, but this is that, so at the 0 we are going to have 2 plus 0 plus TH at the 0, so of course TH at the x equals 0 is 0. And then 7 is the other boundary condition, which is the temperature at x equals 5. But if we put 5 here, we are going to end up with 2 plus 5, ground color, 2 plus 5 plus the temperature H at T5. Well, the boundary condition then on the other side for the function th on the side x equals 5 is also 0. Okay, so what is the so from those conditions we know that then we know that th of dx has to be given by the sum from n equal 1 to infinity of coefficients Cn, and now we have exponential of -3 because this is the thermal diffusivity, n pi over 5 because that's L square T, and then sine of n pi x over 5. What are the coefficients Cn? The coefficients Cn are given by the initial condition. Oh, I forgot to write what are the initial conditions. The initial condition for this problem is, recall initial condition, let's put it here. Initial condition is that the function temperature, tau of x, is the temperature at 0x. But this is actually 2 plus x plus the initial temperature of th. Well, from here we see that the initial temperature for th is nothing more than tau minus 2 minus x. So when it comes to compute the coefficient Cn, what we need to do is evaluate this at 0, so the exponential is going to disappear, and then we are going to have t h at 0x. On one side is going to be the sum from n equal 1 to infinity of the coefficient Cn multiplied by 1, and then multiplied by sine of n pi x over 5. But on the other side, this is equal that, so it's going to be tau of x minus 2 minus x. So what is the formula for the coefficient Cn? Cn is nothing more than the 1 over the integral from 0 to 5 of sine square of n pi x over 5 dx. So this is the length of these eigenfunctions times, there we go, times so what we are, let's go a little bit slower. What we are doing, what we need to do to compute this coefficient is we need to multiply this whole equation, so this whole equation here, by sine of m pi over 5x and integrate, and because the sine of n and m pi over x are orthogonal, what we are going to get is an equation of the form the integral from 0 to 5 of tau of x minus 2 minus x multiplied by the sine of n pi x over 5 dx. This has to be equal only the coefficient Cn, and here we are going to have only 0 to 5, the integral of sine square of n pi x over 5 dx. Why is that? Because recall, because the integral from 0 to 5 of sine of n pi x over 5 sine of m pi x over 5 dx, this is equal 0 when n is different from m, because the sine functions are mutually perpendicular. So we know that this integral here we have computed in previous videos, and this is independent of n, and this is just 5 over 2. That is what we are going to get by using a trigonometric identity. So we have a very nice formula for the coefficients, which is the formula in the theorem. Cn is nothing more than 2 over 5, the integral from 0 to 5 of tau minus 2 minus x sine of n pi x over 5 dx. So we need to do this integral, and we are done. We solved the problem. So how we compute this integral? Well, we have what tau is. Tau is right here. It's a constant function up to, this is what? This here is 5 over 2. So what we need to do is split the integral from 0 to 5 over 2, and then from 5 over 2 to 5, because we have two different values for the function t in the different sides of the interval. So what we do is Cn is going to be, we still have the 2, 5 in front, and now we are going to have the integral from 0 to 5 over 2. In that interval, from 0 to 5 over 2, so only here, the function tau is just 2. So we can replace it by 2. And then we have minus 2 minus x. Okay. Sine of n pi x over 5. Then we have to add the integral from from 5/2 to 5 of the same function, but between 5/2 and 5 the function tau takes value 7, so we can replace this function by 7 in this side of the interval, minus 2 minus x sine of n pi x over 5 dx. Okay. So obviously these two cancel out. Obviously these other two give me a 5. And then we have the two terms with x. So let's see, what do we get? We get the 2 over 5 is always there. Then we have the integral minus integral from 0 to 5/2 of x sine of n pi x over 5. This integral is only from 0 to 5/2. Then we have 5, which we take it outside, common factor, from the integral from 5/2 to 5 of sine of n pi x over 5. What happened here? There. What is that term? Well, the 5 here multiplied by the sine. But then we have another term that is minus x multiplied by that, so I'm going to put it here, also integrated from 5/2 to 5. So let me put here minus the integral from 5/2 to 5 of x sine of n pi x over 5 dx. Okay, but notice that this integral, the integrand here and the integral here are exactly the same, so this integral from 0 to 5 half of that and from 5 half to 5 of that can be combined into one integral, and then the formula for the coefficient Cn is a little bit simpler, is negative 2 over 5 integral from 0 to 5 of x sine of x, actually sine of n pi, this is a pi over 5 dx. I combined these two integrals, I combined these two integrals, integral from 0 to 5, and then we still have that term that, well, is still there, and recall is multiplied by the 2/5, so the 5s are gonna cancel out, and they're gonna get only, I'm gonna get only a 2 integral from, and this integral is only from 5 half to 5, and we have the sign here of n pi x over 5. So this integral simplified a little bit, so now we can actually do the integration. And to do the integration, we need to recall a formula of integration by parts, which says that x sine of ax dx, this is always negative x over a cosine of ax, and then plus 1 over a squared sine. This, by doing two integration by parts, you get this formula, and we are going to use this formula with a equal n pi over 5, and we are going to evaluate everything at 0 and 5. And on the other integral, well, it's the integral of the sine, so this is easy. That is the complicated integral. Okay, let's use all that, and we get sine Cn. What is Cn? Well, we still have the negative 2/5. Okay. Then what do we need? We need minus x over a, so 5 over n pi. There. Then we have a cosine of n pi x over 5. Then we have plus 1 over a squared, which is going to be 5 squared over n squared pi squared sine of n pi x over 5. All that has to be evaluated between 0 and 5. And then we have one more term that is 2. Then we need to integrate the sine. Which function the derivative is sine? Well, that is minus cosine, so we are going to have minus 5 over n pi. Then we are going to have the cosine of n pi x over 5, and this cosine has to be evaluated only in 5 half and 5. All right. Almost there. So we still have a negative 2/5. We keep it outside of the first term. What happens when we evaluate at 5? Well, we are going to have a 5 here, a 5 here, so, and a 5 there. So we are going to have minus 5 squared over n pi, not squares. Then we are going to have the cosine of n pi, the 5 cancel out, plus 5 squared over, and here we have n squared and pi squared. Then we have the sine of n pi. Alright, this is the evaluation at pi. What happens when we evaluate at 0? When we evaluate at 0, we have a big 0 here, so disappears. And also sine of 0, which is also 0. So we are going to get minus 0, minus 0. Good. And on the other term, we still have minus 10 over n pi. You see this here is a minus 10. Then we have the cosine of n pi minus the cosine of n pi, and then half over 2, so pi over 2 here. Okay, that is when we evaluate at pi over 2. Good. One further simplification. Here, this sine of pi is actually 0, and the cosine of pi in both terms here is equal -1 to the power n. This is, we could simplify, but it's more complicated, so we leave it as it is. So, oh, but notice there is one more simplification that I failed to see, but now it's going to be easy to see. Before we, so we are going to make this 0, because this is 0, it's silly to keep it there. This simplification, we are going to do it a little bit later. And actually we are not going to need to do it, because look what happens. Recall this this factor goes here and then goes there. Oh, sorry, that is 0, so only goes there. So we are going to have negative is plus, one 5 is going to cancel, and the other is going to make a 10 over n pi, and then we have a cosine of n pi. Okay. Then this is 0, 0, and then minus 10 over n pi cosine of n pi. The same thing with the opposite sign, and then negative is positive, 10 over n pi, and here we have the cosine of n pi over 2. And this term goes with that term. Alright, so after a lot of simplifications, Cn, the coefficient Cn, resulted to be really simple. N pi cosine of n pi over 2. And here half the terms are 0, the other half are different from 0. But we leave it as it is enough for us. So this is it. So, well, we could do the simplification if we want to, but let's do the simplification. What happens when n is even? Then we have cosine of 2k pi over 2, which is cosine of k pi, and this here is -1 to the k. What happens when we have n equal odd to k minus 1? Then we are going to have cosine of 2k minus 1, so an odd multiple of pi over 2. Well, these are always 0. So what happens is the half the coefficients here, or half the coefficient, there it is. Half the coefficients are 0, the other half are -1 to the power k. So we can say that C2k minus 1 are 0, and C2k are of the form -1 to the power k 10 over n pi. Very simple. Half the coefficient are 0. It's important to put this simplification so the final formula is simpler, because now what we get is that the temperature as function of time and position is going to be the equilibrium solution 2 plus x plus the sum for all n, but half the n are 0 and the other half are different from 0, so we are going to call them k from 1 to infinity, and these are the only coefficients that are non-zero, so they are going to be they are going to be what? Oh, there is a little problem here. 2k, and then I should put here n equal to k. So let's write it down. This is actually, well, 2k. Oh, there is one simplification now, because this is -1 to the power k. The 2 with the 5 is going, the 10 is going to make me a 5 k pi. That is one little simplification. So we can put this coefficient here, -1 to the power k, then 5 over k pi, and then the exponential -3, then n squared, but this is 2k pi over 5 square, and then sine of n, which is 2k pi x over 5. That is the solution. So by translating by the equilibrium solution and doing some non-trivial simplification, we get a very simple formula for the coefficients of this and for the whole solution. And this is how we use the translation of the non-homogeneous boundary condition problem into an homogeneous boundary condition problem. We solve the homogeneous and then we adapt. This is the equilibrium solution. This is the solution of the homogeneous problem. Oh, I forgot something. There is a t here. So when t goes to infinity or t grows, this part of the solution goes to 0. So this whole thing goes to 0 and the solution goes to the equilibrium solution. But there is a transient, a time-dependent part, which is what we call, this is what we call the TH. TX. Alright, that's enough for today. See you guys in the next video.